Won't you all just say hello to Matsadiso? We're going to, I forgot to video lessons for her on that practical on reaction rate. So what we'll probably do is just ask you to explain it. How about that? So it was a practical on reaction rate, and you are writing up your experiment. Okay, so what does every experiment have? Aim. Hypothesis. Method. Results. Conclusion. A graph somewhere in the results. And then possible diagram of your apparatus. And then don't forget you're going to get muchas marks for. What are you going to get a lot of marks for? Discussion. You're all going to earn marks today for helping. Those who haven't already helped, because we're going to be doing after this titration experiment, which will be your last experiment for marks. I gave you the worksheet. Now, what must come in your discussion? Now, Matsadiso's got the results. I think I put them on Google Classroom, and no one corrected me. It was 8 seconds at 46 degrees. It was 80 seconds at 80 seconds at 18 degrees. Was it 17 degrees? And then at 46 degrees, it was 8 seconds. Okay, so those, you've got a nice little, not straight line graph. Then you're going to get most of your marks from the discussion. And I said there's two graphs in the discussion you must discuss. They're called the Maxwell-Boltzmann one. It's the one that looks like this. Time, energy. So that's the one graph. You must explain how temperature plays a role. Remember, this is your activation energy. This is the energy of the reactants. This is the energy of the products, or whatever. But it's got to get over this activation energy hump. And the more energy you give the molecules, the more they can get over that activation energy hump. Then there's a second curve that looks like this. That's the one, and this is the other. Now, it's the number of molecules with sufficient energy. I think one of these graphs is the one when it's hot, the molecules are hot. So we've got a sort of I'm just going from memory, I'm a little fuzzy on this. This is the one graph, this is the other graph. Now, which of these populations of molecules? So this is energy, and this would be number can react, something like that. And here's your whole population of molecules. What happens when you heat them? Well, more molecules have enough energy to overcome the activation energy. So this would be your graph if you heat it. If you don't, it's something like that. Anyway, would you mind just looking over it in your textbook? It's that graph. This would be when you don't have enough molecules that can react, or so the population of molecules that can react is just a small number, something like that. I'm going to sound terrible on video, but it's been a while since I looked at that. But those are the two that you have to discuss those. Okay. So, are we happy? Any other questions regarding what must go into your write-up on that reaction rate? Remember, we also said fair test. How do we keep the three things we did fair? The same amounts of solutions A and B. We treated everything the same. We always try to keep, and we throw them and we start the stop clock the same way. We measure the end, it turns black. Okay, that's easy to tell. I think there was just one. That was the cold one. When I looked at the video, it actually started turning about 20 or 15 seconds before. Just started to turn a little bit black, and then it was halfway black when we hit the second hand, hit the 4-minute mark. So maybe that one would have been a little bit difficult to say when exactly it finished. What you're supposed to do is when you throw A with B, you're supposed to shake it, to mix them. If you don't, A sits on top of B, or whichever one you threw in last. And then it turns black at the border, and then it slowly spreads. Now that doesn't matter when you do it at hot, it just boom, done. But when you do it at cold, it spreads slowly over about half a minute. That makes it harder to tell when the reaction ends. But fair test, you must mention that. And yeah, did you enjoy that practical? Yeah. Okay, and then, oh yeah, don't forget you've also got to discuss the nature of the reactants. What was in solution A? What was in solution B? Does anyone remember what was in the ones? Peroxide and sulfuric acid. Well done. What was in the other?
Starch and potassium iodide.
Potassium iodide. Starch.
And sodium thiosulfate.
And sodium thiosulfate. Great. You see, guys, if you know from memory what we did, fantastic. This is all we ask of you in class. You notice the notes are not that great. I expect you to kind of keep it up here, so well done. Okay, and then what was it that slowed it down? What was the one chemical that slowed down the whole reaction? The sodium thiosulfate, correct. So it ate up the iodine as fast as it was produced, and when the sodium thiosulfate ran out, the iodine formed, turned the starch black, boom. So you can control the rate of the reaction by the amount of sodium thiosulfate. And so I played around before you guys came and we did it.